So our next presenter is McLain with DGI Geoscience, and if you didn't know, right now they're about the only group in town that does downhole borehole geophysics. So they've got an outfit based out of Salt Lake, right? And they cover Utah and other areas in the. Well, I think you cover the whole country, right? But you have a
whole world.
So
mostly U.S. and Canada. Yeah.
He's going to be talking a little bit about some general borehole geophysics stuff, but mostly about some new technology that can be used in relation to drilling water wells, being able to describe them and understand them even more. So I'll turn the time over to McLain. Thanks.
Thank you, Jim. Yeah, I'll cover new technology. Jim wanted me to do an overview of the traditional technology too, for anybody who's not familiar. So I'll cover both of those. And if you are familiar, I hope I don't bore you with the old stuff. But just wait till the end. You'll see some new stuff that hopefully you're not more experts on than I am. But DGI used to stand for Downhole Geophysics Incorporated. They had a merger and then unmerged, and they had some new skills, so they didn't want to limit themselves to that. So they added Geoscience on the end and made the DGI an acronym. So now if you extend it all out, our company name is Downhole Geophysics Incorporated, Geoscience Incorporated. We've been around 25 years. Our headquarters is actually in Toronto, Canada. We always worked down in the U.S., so we incorporated in the U.S. 3 or 4 years ago. First in Elko, we do a lot of work in mining. And then through Bingham, we got some work over here, so we opened an office here in Salt Lake. And we currently have 5 technicians running 3 trucks. And happy to be here.
I thought DGA stood for darn good engineering.
Yeah, that too. That's right. So let me see, how do you... So just a quick overview for anybody who hasn't run a wireline survey on their rig. The overall concept is borehole geophysics is just using electronic sensors to put down a hole to measure information about the formation, the water, the borehole itself. The traditional setup is shown there on the left with a truck with a wire line coming out the back, hooked to a shiv wheel on the mast of the rig, down to the probe. Now, the probe isn't usually as tall as the rig. That's just a little zoom in there so you can see what we're talking about. But we have done a couple holes where we've stacked a bunch of probes together, and it's been almost as tall as the rig mast.
Inside the truck, are there a bunch of monitors and
Yeah, well, I got there's a picture there.
agents and stuff?
Yeah, just usually one CIA agent, but yeah. So the sensors are, of course, housed in a steel probe for protection, waterproofing, and they're usually lowered down on a wire line. You don't have to use a wire line. There's other systems that can just be deployed down to latch onto the bit and poke out through the bottom. And then as the driller pulls the rods, it just measures the formation on the way out. There's systems that go down on tubing, like flexible tubing. There's systems for surveying up a hole, having 2 wire lines in the hole, one to pull the probe up and one to survey it down, like if you're in an underground mine and you want to survey something from beneath. But the most common system is to have a conductive wire line. It's got a copper conductor in the middle that transmits data. So the advantage of that is you can see the data immediately at the surface in real time. And what you usually see is a graph like this. It's just a depth track, 10 meters, feet, whatever. And then the parameter you're measuring with low response on the left and high response on the right, and then a squiggly line just indicating the response of the formation at each one of those depth slices. And you can put the depth slices whatever you want. You can measure every millimeter, you can measure every foot or bigger. It just depends on the resolution you need and how fast you want to run. The faster you run, the lower the resolution. I keep forgetting. Here's just a real truck instead of a cartoon of a truck. It's just cleaned up all nice for the Elko Mine Expo a few weeks ago over in Nevada. And a picture of a probe. This is actually 2 probes together. This bottom one here is a televiewer. That's an imager. It just images the inside of the hole, and it can see through casing to see cement and bentonite behind. And then on top is a resistivity probe, which is very commonly used, and I'll talk about that in the groundwater industry. And then on top of that, you see this orange insulated cable. For resistivity, you can't have conductive cable in the vicinity of the probe, so the start of the wire line is insulated, and then that just hooks into the normal wire line.
What are you measuring with the resistivity?
Well, I'm going to talk all about it, but it'll just the resistivity of the formation, the electrical resistivity. Yep.
Seeing the inside, I can see why there's only one CIA.
Yeah. Well, this is a smaller.
Otherwise,
This isn't that same truck. Yeah, this truck's bigger, but this is actually a van, more mobile. And so, yeah, you just got the winch down here, the wire line going out to the rig, and the CIA monitor here. We only have one showing the readout. It's sitting on top of our probe rack. That's just a compartment with PVC tubes that are padded that we can stick the probes into for transport. And then the rest just shelving, flame cabinet, heater. Here's just a picture of us in action, just backed up to the rig, wire line shooting out the back, going down the hole.
It's one of the longest wire lines you've ever seen, Bill.
Well, you know, the longest we have is about 2 miles, but you know, oil jobs like Schlumberger, Halliburton, they go more than that. I used to work in the industry. I guess the deepest well log I ever looked at was only a couple miles, but there's got to be deeper than that, yeah. And that was mostly horizontal. They weren't drilling 2 miles straight down. They were going down and then kicking off. So a little history, just for the classical history buffs here. Borehole geophysics has been around about 100 years. It was invented in France by the Schlumberger brothers, Conrad and Michel. Their objective was looking for oil, and their system, this isn't the earliest system right here. The first system was just a hand-cranked winch, and the data was measured stationary, and these guys would just read the data out, feed out, and just mark it on a piece of paper, and then they'd connect the dots, and that was the log. They were only running one measurement. It was a resistivity measurement, but a very basic one, just 1 point down the hole and 1 point at surface, and just measuring the voltage difference. And oil is resistive, whereas most oil deposits are not in fresh water. If it was in fresh surface water, it would have bubbled up and escaped to the atmosphere. It's in salt water, so salt water is conductive. So in this particular well, probably the oil zone might have been right here. This might be high resistivity just because it's dry up there. And their slogan, I thought this was interesting. They called their service, it wasn't called borehole geophysics, it was called electrical coring, because back then, as today, core drilling is expensive. So they were trying to sell the concept that you can use what we give you instead of core drilling and get everything you need. And of course that might not be totally true, but interestingly, still today in France, the term for borehole geophysics is carottage électrique, which means literally translates to electrical coring. So I guess it.
Electrical was a buzzword.
It's a good one. So it worked out, their slogan. So quickly, the applications for groundwater. I'm going to touch on these three in most of the talk, so I'll just go through them quick. Delineating fresh from saline water, just like how they delineated oil from saline water. Fresh water is resistive, saline water is conductive. Evaluating lithology, like sandstones that will transmit groundwater, shales that are tight won't transmit groundwater. Related to that, determining the porosity and permeability of the formation. And then I'm just going to show a few examples of things that I'm not going to have time to touch on. So I just want to just give a quick example of some other applications. Measuring flow and fluid pathways. So what you're seeing here is a flow meter. It's just measuring the vertical flow in the hole as you pump, or you can inject. And some of these are just derived things, but the main log is right here, and you can see high flow up here, that's 94 gallons a minute, but it drops off to 55 gallons a minute. That's because as you're pumping up, the suction is now, it's trying to go straight down the hole, but there's a big fracture there, and there's water coming in the sides. So you're getting that suction is now acting to pull water in and not just up. So the upward flow rate below there drops, and you can just subtract the flow rate above and below and know how much is coming in. It's 39 gallons a minute.
So are you just stopping, like, say, every 20 feet?
No, it's continuous.
reading?
No, you just continuously run. And it's just got a little propeller on it. Well, there's different types. The most basic one, just a little propeller on it, and you're just measuring the spin rate. And so it's usually called a spinner.
Subtracting it from the rate that you're...
Yeah, well, at the top it's spinning. Say it's proposed that does like one, just for simplicity, 1 RPM is 1 gallon a minute. That means it was spinning at 94 RPMs there, and it's spinning at 55 there. So that's 94 and 55, and the difference.
So see, you'd get your difference would be okay, but I mean, that wouldn't be an accurate reading if your probe is moving, unless you were taking that into account somehow. Is it moving very slowly, or?
No, it's moving. I mean, you would calibrate the RPMs, like I was telling you, to what you would get at 1 gallon per minute upward flow, moving at a set speed downhole.
Okay, so you pre-calibrated that.
Yeah,
Okay,
yeah,
so
sure.
it is factored in.
Yeah. So this is more for fracture-driven flow, obviously, limestones, hard rock, like maybe dewatering at a mine. Measuring water quality, that's pretty self-explanatory. This is just pH, conductivity of the water, temperature, pressure, dissolved oxygen, redox potential, and you can just measure down the hole. You can see there's something happening here. Maybe that's an inflow of contaminated water or something. And then imaging. This is just that imager that I showed you a couple of slides ago, the televiewer. And what you're seeing here is just a picture, an acoustic picture, just using sound waves, of the inside of the casing. That's pretty mundane. You can see some spots here. That's probably just some pitting on the inside of the casing. And then behind, it can see behind the casing. And what you're seeing here is cement and bentonite. Cement's more reflective, so it shows up brighter. Bentonite's more absorbs sound, so it's darker. But of interest, right here, there's a dark spot in the cement, and that's a void in the cement, which, as you know.
So are you using X-rays to look through the casing, or how are you doing?
No, it's just sound.
Oh, sound. I'm sorry, you said that.
Yep, just ultrasonic sound frequency. You just record how long it takes to bounce back and how loud it is. How loud it started with, and if it comes back just about as loud, then it hits something hard. If it comes back quieter, then it hits something soft.
Rings or bumps.
Yeah, yep. And so,
You said something about the oxygen. I'm sorry.
oh, I should be repeating your question, shouldn't I?
I'm
Yeah,
just-
forgot
just
about that.
finding this interesting.
Uh-huh.
So when you're measuring the dissolved oxygen, how are you doing that? What kind of sensor are you using for that?
It's a chemical sensor. I actually don't know how the dissolved oxygen is measured.
For scuba diving, you measure the oxygen in the air that you're breathing, so you don't run out of air. And they use, what do they call it? Anyway, it's kind of like a battery, a dry battery.
Huh. Yeah, I'm not sure actually how the oxygen's measured. There's actual chemical standards. There's liquid chemicals that are in the probe, so it's always measuring against that. So I think it's probably like a galvanic electrical comparison between the formation water and the standard in the probe. But
Oh, okay, so the water it would be similar to the one that you use for in the air then, because what you're doing there is like say you've got zinc, the dry zinc battery or dry aluminum battery, and like a hearing aid battery. And so how much oxygen you have in the air determines how much voltage it puts out, how much average it puts out. So you have something to measure.
okay, yeah, I'll have to look into that.
One
Yeah,
too,
yeah,
on how you design that so you get the flow through.
yeah. I'm not sure. That'll be my next talk. I'll have to look more into that.
I want to look into that too, that sounds interesting. Anyway, thanks, I'm sorry.
Yeah, no problem. No problem. So yeah, these are just some examples. There's many, many more techniques that I won't go into. There's standard things for measuring cement contact behind casing. That you might have heard of a cement bond log. That gives you an average of the entire bond between the casing, the cement, and the formation. But the advantage of this imager is you can actually see it and see the nature of any sort of bad bond. So I just plan to talk about 3 probes today, just 2 of the traditional ones and then 1 new one. And I'll just give you an overview of the physics of it, how it works. I think that helps in understanding the measurement. And then look at the data and how it's interpreted for groundwater. And then there's a data set that we collected in the Salt Lake area that we have all these probes on. So we'll interpret that one together as we go. So the most basic probe I'll talk about is just gamma ray. All it does is it measures radiation in the formation, which, as you might know, rocks actually are radioactive. And there's 3 elements that in nature cause radiation: potassium, thorium, and uranium. In groundwater, we're mostly always worried or seeing potassium. If you have uranium in your hole, that's probably bad. Uranium is very soluble in water, so that means you're going to be drinking uranium. That it's not good. And thorium is mostly in granite, igneous rocks. So the way it works, there's a scintillator crystal. That's this little thing. I'm not exactly sure how it works, but what it does is it takes a gamma ray. When it gets hit by a gamma ray, it just lights up. And so the light then gets converted by a photomultiplier, which converts light into electron flow, electrical pulses that can be measured with an electrical device. And the more pulses you get, the more radiation that was in the formation. Pretty basic, pretty simple. The data then, the raw data is just in counts per second. So how many radiation pulses you're seeing per second in whatever your resolution is. If you wanted to measure every inch or every 6 inches, it'll just give you a curve with counts per second. Now to point one important thing out, the gamma ray probe is statistically constrained, and that means that it's at the mercy of these potassium elements shooting out radiation, and that's not a regular thing. It's a random process. So sometimes they're going to emit more radiation than normal. Sometimes they're going to emit less radiation than normal. And so if the only way to mitigate that is either take your sample size that you're averaging over and make it bigger, or run slower. But if you're going to try to run 1 millimeter resolution and zip the probe up, you're probably going to not be getting very good data, because you're going to be just measuring whatever mood the potassium was in at that point, if it wanted to shoot out more or wanted to shoot out less. But if you take a bigger sample, you stay in it longer, the law of averages will average out and you'll get a representative sample. One real nice thing about gamma is it works through casing, it works open hole, works in fluid, works in dry hole, because gamma rays don't care, they'll go through anything. They can get more absorbed if you got more rock and more casing and more cement between the probe and the formation. They will get absorbed. So you'll only get relative data if you got a bunch of cement in the way, but that can be corrected out. So gamma is pretty versatile. It can give you anything, or work in most situations that we're going to encounter anyway. And lastly, it has to be calibrated. That scintillation crystal, it degrades over time. And so for the same formation, a year later, it'll actually be measuring fewer counts per second. So to calibrate, it's really easy. There's just calibration holes, like there's some down in Grand Junction that are controlled by the DOE. They put those in for uranium logging, for measuring, for looking for uranium. And you see, you know how much radiation it's emitting, you see how many counts per second, and you just write a new calibration equation that relates counts per second to the standard unit, which is API. It's because American Petroleum Institute are the ones who came up with this whole idea and put the standard in place. So if you see a log and it's an API, it means it's calibrated. If it's in CPS, counts per second, it means it's not calibrated, and it's just giving you relative data, high and low. So how do we interpret it? For groundwater, well, gamma is higher in rock types that have a lot of potassium. Sandstone, silicon dioxide, that's it, no potassium. Carbonate, carbon trioxide with iron, calcium, or magnesium, no potassium again. So sandstone, SS, DOL for dolomite, which is a common carbonate, have low gamma ray. So low is over here, high is over here. Shale, on the other hand, has clay minerals in it. It's the textbook definition, 65% clay. And that is, most clays are high in potassium. So shale tends to have high gamma. Why is that important for groundwater? You probably, many of you know this already, but clay has very, very small pores. And so it could have high porosity, but the pores are so small that there's low permeability. The water can't flow through it. This is the effect, quartz, so sandstone, quartz, the permeability, which is on the y-axis here, low to high, versus the porosity, so how much space of that rock is water. As porosity goes up, permeability goes up too. But if you just add in 10% clay, it goes down 2 scale units, which this is logarithmic scale, so that's 100 times. So 100 times less permeable with just 10% clay. Now in this graph, it's pretty well behaved. You have 100% shale and 100% sandstone and perfect boundaries between the layers. That doesn't always happen in nature. So the way we interpret a log is simply look for the maximum gamma, mark a line there, call that your shale line, and the minimum gamma, call that your sand line, or if you're in carbonate, you can call it your limestone line. And then anything in between there, you just use the gamma value to estimate the amount of it that is shale. So here's the example from...
You have to get your percentage of fines in that soil if it's in the clays and there's a certain distance over. Would you be able to say there's the permeability is X? And
You could, I mean, yeah. I haven't seen a he asked if you can estimate the number of the percentage of fines and permeability based on gamma. And well, you do get a very good indication of your clay content, which is going to be fine material. Bentonite, like from in the drilling mud, that looks like clay. So but are you talking about like invasion of the bentonite into the formation?
the permeability of it, so you can define if it's confining or not, just cutting it. Like if we're building walls, we want to cut some units off. How would we're looking for clays that has low permeability that we can build a wall into, like a bathtub. And so we're looking to see how.
Yeah, I think you could. I haven't seen much quantitative estimates of like permeability from gamma, but qualitatively it would correlate, yeah. And the last technology is really what you probably should use for that. And so maybe you'll have a better answer at the end. So, you know, obviously this data is a little less cut and dry as that textbook example I showed you, but I scaled it so that the left side is the minimum, which is 40 API units, which is pretty typical for a sandstone. The maximum is 100, which is pretty typical for a shale. So we can just draw a line on what is basically our minimum there, call that sand, and draw a line on the maximum, call that shale. And then everything in between is gradational. So you might have kind of dirty sand, or up at the top there where it's jagged like this, you probably have shale sand sequence, like from a river that might have been migrating across the floodplain. First it deposits shale, then sandstone, then it comes back the other way. So you have layers. Now let's look for where our potential aquifers or transmissive zones that we would want to produce from might be. Well, based on this, you want to look at the sands, the low gammas. So one is right here. That's probably the thickest zone of relatively low gamma. So it's probably the thickest sand zone. And then one up here has even lower gamma. So it's going to be really, really clean sand. And because of that, it should have the highest permeability on this log anyway. Sorry, I was trying to. So I mean that's the whole interpretation of a gamma log. You could pick your packer zones just based on that. Develop your well, set your screen intervals just based on that. But there are some exceptions. You know, gamma. There are some clays that are not high in gamma or not high in potassium, so they have low gamma. And there's some sandstones that can have some feldspar in it, so that's going to have potassium. So you can have sandstone that has higher gamma. So you always want to have more than one piece of information to go off of. So that's why we almost never run just a gamma log. The next most common one that we run is that resistivity log. And the way it works is it just puts a positive electrode and a negative electrode down the borehole, and you just pump current in between them, and you measure the resistivity of the formation.
I bet you could sell more of that if you added the word electrical to the front of that resistivity. Electrical resistivity.
Oh, okay, thank you. I'll do that.
Buzzword.
Yep. So here's the positive electrode. The negative electrode is beyond the probe. It's actually at the top of that orange insulated cable that I had in one of the first slides. I didn't have enough room on the slide. I mean, actually, it'd be way up on the ceiling or higher than that. But it's had an infinite symbol next to it. That's a geophysical concept for the negative electrode being far enough away from the positive electrode that the current right near the positive electrode doesn't feel the force from the negative electrode pulling on it. If it did feel that, if it was close, what it would do is it would just flow straight up the hole, because both these sensors are in the hole, and you just measure the resistivity of the borehole fluid. And we already know that. We don't want that. It's not what we're looking for. So they put it far enough away that the charge, as it comes out of that positive electrode, just flows out evenly, because it's just being pushed out from one point. And so the flow looks like that. Of course, this is a circle, but it's going out spherically in all directions. Yeah.
Just for clarity, are we talking primarily uncased hole?
Yeah, sorry. Resistivity, it'll work in a cased hole, but it'll just give you really, really low resistivity. So yeah, you have to run this in open hole.
Depending on whether it's steel or PVC.
Yeah, you could run it in PVC, it'll give you really low resistivity. We can run it obviously in slotted PVC. It gives you room for the charge to get into the formation. It will mess with it. It'll be higher resistivity than if you were in an open hole. But yeah, generally this is an open hole, and you have to be in water. The current can't, air is a really, really effective insulator. That's why, yeah.
So why would you put your negative up the hole rather than just have it at the end of your wire that you're spooling out?
The end of the wire meaning, well, the end of the wire is right here. It's attached to the probe, so that'd be too close.
Well, no, but there's got to be another end of the wire. Where
Oh,
you
at the top,
read it.
with the winch?
Yeah, well, or back at the end of the wire that is coming off your reel.
That's a factor of how much power you got to put out.
Well, the old systems actually, yeah,
Because if you go down, if you're pulling off of a wire as it goes down, your resistivity along that wire is changing all the time, depending on how much wire you've got down there.
well, the wire doesn't matter because it's all insulated.
Yeah, you've got a break above your negative electrode. It's not going to go up your cable going up to the top.
Yeah, it's all, and the probe's insulated too, so I mean,
You're looking at point A and point B, what you're trying to get data between. You don't want
Problem is it'd be
3,000.
above the fluid level, and so then
Yeah.
it makes it inaccurate. You've gotta have, both probes have to be in fluid.
well, the early systems buried a negative electrode at surface, but they dumped water on it. That's not as effective. I mean, getting that negative charge into the rock and being able to interact with downhole, way down the hole, it doesn't make as good a contact. And this might be kind of what you're getting at. Then the distance between those electrodes is changing as you move the probe up in the hole, if you got one sitting at surface. And so it's not a big effect, but it can have a small effect on the voltages that you measure. So we put it just both in the hole. They're always the same distance apart, but they're insulated. So there's,
They move together, okay.
yeah.
All right.
So the charge goes out spherically, equally in all directions. And so the only force that's acting on the charge effectively is that positive electrode. So that's an expansive force pushing out in all directions, and the only thing that that resists that flow of electrons is the formation. So the more resistive the formation, the harder it is for the charges to expand. They get concentrated in a smaller area, and that builds up voltage. More charge concentrated, higher voltage. So how do we measure resistivity? Well, first we measure resistance just by measuring that voltage. Just put a voltmeter on the probe at a certain distance from the electrode, and just basic Ohm's law of resistance is voltage over current. We control the current because we're hooking it up to our generator, powering it, and we measure the voltage, do the division, and you get resistance. However, if you then were to take your voltmeter and move it a different place on the probe, you'd measure different voltage, because as the charge spreads out, the voltage drops.
I'm sure you got this figured out, or somebody did this, but why are you varying the amount? Why are you regulating the current and measuring the voltage instead of regulating the voltage and measuring the current?
I think you probably could do that.
I mean, the reason I ask is because if I were going to try to do something like that, it would be like the simple thing to do would be hook it up to a car battery, or if that wasn't enough voltage, a bank of car batteries to get the voltage you wanted. But that way it'd be constant all the time. Whereas it seemed like with the current, you'd have to pump out enough to, I don't know, how would you keep that standard? How would you keep that the same all the time?
Well, you know what it is all the time. It's not necessarily the same all the time, but it's known.
Oh, no, nothing's magic. If it's magic, somebody's pulling over on you.
Well, you can measure it. You know what it is. Yeah. Yeah. You probably could do it you could do the whole thing in reverse. You probably could. And I don't know why the Schlumberger brothers did it this way, but that's the way they did it 100 years ago. So, yeah.
So you're telling us this works then?
Yeah, well, you'll see. Yeah, we'll see. It works great. So to account for the distance that you put the voltmeter, as I mentioned, if you move it up, it's lower voltage, you're going to get a lower resistance. And so all you do is you multiply the resistance that you measure by the distance between the probe. And so then if you move this voltmeter anywhere on the probe, it'll move it up, it'll have lower voltage, but it'll have a higher distance and they even out. So you'll measure the same resistivity. And so multiplying the resistance times the distance, that's ohms times meters. So the units for resistivity are ohm meters. So theoretically, you should have, well, the standard is to put 2 voltmeters on the probe and measure it at 2 spots. The standard is 16 inches and 64 inches. And like I said, they should even out. They should, in theory, give you the same answer. In practice, they don't usually give you the same answer. And why might that be? Because if you look at the 16-inch, it's interacting with, and it depends on the hole size, but it's interacting with as much borehole fluid as it is formation. So it's averaging the formation and the fluid. The 64, on the other hand, is measuring mostly formation, just a little bit of borehole fluid. So the 64 technically should be the more accurate measurement. But then what if you have this? A layer of rock that's thinner than the volume that you're investigating. Then the 64 is just going to average it all out, and so it loses resolution and accuracy. So the reason for the 2 points is 16 gives you high resolution, and 64 gives you a more accurate resistivity of the formation as a whole.
How do you tell them, as you're moving through things, which kind of situation you're in?
Well, yeah, I think I'll probably explain that.
Okay.
Yeah.
When you're looking between those 2 points.
Yeah. How do we interpret resistivity for groundwater? Well, as I mentioned earlier, the primary control over resistivity is the borehole fluid. More saline, less resistive. However, in groundwater, we're hopefully most of the time going in freshwater, or most of the time we're going to be drilling in freshwater. And so if the formation water is the same, the next most important factor is the minerals, and clay has conductive surfaces. That's just illustrated here with this little static electricity things on the clay. The crystal chemistry of why that is, I'm not going to go into, but just know that clay is more conductive than sandstone or carbonate. So if we were to plot this different rock types on a graph where the fluid, the formation water conductivity is down here, low to high, and the formation overall, including the minerals, is on the y-axis, again, low to high. Fresh water would be over here, the low conductivity, high resistivity fluid, and clay would be, on this scale anyway, somewhere in the middle there. Sandstone would be far down, it's not very conductive. An average drilling mud would be up here. Of course, that depends on how much bentonite you've got on it, polymer, if you're drilling with brine or anything like that. But just representative drilling mud, generally more conductive than clay. If we move over to saline water, the drilling mud's the same, assuming we're using the same drilling mud, but the sandstone and clay conductivities are going to shoot up. And again, this is a logarithmic scale, so that's exponentially increasing as you increase the salinity of the formation. So you can see in freshwater, clay and sandstone have a large contrast in their resistivities. In saline water, they're a lot closer and overall lower resistivity, or in this graph, higher conductivity.
But in salt water, if it was very concentrated at all, it would just swamp all that. It would wipe out any.
Yeah, well, if you keep going, these probably converge. If you keep going to more saline, you see how they're getting a little bit closer? They actually would, the formation water would just dominate. Actually, interestingly, see clay actually hangs on to its resistivity longer than sandstone. That's because it is conductive, so it plays a bigger role. Whereas sandstone, not conductive at all. And so as soon as you add a little bit of salt water in there, that's just going to start to take over and drive the conductivity.
It would be interesting if you had another line on there that just showed what the conductivity is was of the saline alone.
Yeah. Well,
Would it
you mean
parallel-
just salt water?
Would it, yeah. would
It'd just be a
parallel
it'd just be a
those
straight line. It'd just be 10 to the negative 3, 10 to the negative 3, 10 to the negative 2. It'd just go straight up.
lines? Okay, so.
Yeah. So let's just look at a couple basic responses of a formation. So if we're in fresh water, a sandstone, well, where's our mud conductivity? It's going to be there, white drilling mud. Our formation conductivity, we're in sandstone, so it's going to be here on the sandstone line in fresh water. Our 16-inch, so that nearer to the probe, getting a larger component of borehole fluid into the measurement, it's going to be kind of intermediate between the mud and the sandstone. Whereas the 64, mostly reading the formation, just a little bit of effect from the borehole since it's this bigger area. It's going to be down here by the formation conductivity. So you're going to have some separation. The 16-inch is going to read higher conductivity, lower resistivity. And so here's that data set again. And if we're looking for the sandstones, we're looking for the low gamma. That's here and here. And look at that. The resistivities are separate and they're reading high because sandstone is resistive and we're getting a lot of good separation.
They still follow each other pretty well. That
They do.
picture you were showing, where you had a thick formation through, I got the impression that there'd be a much larger separation between the two readings.
Well, it just depends on what the formation looks like. But no, in general, they're always going to follow each other. It's just you're going to see the 60 or the 16, the screen one, it'll have more curves because it's higher resolution. That 64, it's averaging them all out. So, you know, if you got the two rock types in the same reading, it's just going to average it all out. So there's generally less curviness in the 64 because it's more of an average. And the 64 is generally going to be more resistive because the formation, it's getting deeper into the formation, is more resistive than the borehole fluid. So, but they'll always go in the same direction, or most of the time. So a freshwater shale, drill mud is the same. Now the formation, since shale is mostly clay, it's not all clay. There's some sandstone in there, so it's going to be a little less conductive than clay. The 16 again is going to be intermediate between the two. And again, the 64 is going to be down by the formation. But overall, less separation in shale and higher conductivity overall. So again, if we got a high shale zone indicated by high gamma, very little separation and overall low resistivity. Now that's the standard log, 1664. The one we ran on this well and the one we run all the time has 2 extra volt readings on it, resistivity readings. It's an 8-inch for even higher resolution and a 32. So then that's just what you get. The advantage of this is simply it's easier to see that separation. You know, like, yeah, you can see it, but in some of these zones it's kind of unclear if it's how separate it is. But it's easier to see, like, this separation is very obvious with the additional curves. The other advantage is the red and the black here are overlaying most of the time. That's the 32 and the 64. So since they're telling you the same information, you can infer that the borehole effect is very minimal on those. If it was still acting on one, then they would be separate. But since they're overlaying, it says the borehole effect is negligible. So that's probably your true formation resistivity, is the black and the red. So let's interpret it with the gamma log. Again, where were those zones with the transmissive fluid-bearing zones? Well, here's our low gamma correlates with, that's the lowest gamma indicating the lowest shale, and it's the highest resistivity, again, indicating the lowest shale. Cleanest sand should have the highest permeability in the entire hole. The other one, this thick zone, it was a thick zone of low gamma. So we interpret that to be probably our thickest potential water-bearing zone, and it's also the thickest zone of high resistivity with that separation. So they're in agreement. They're telling you the truth, I guess, because they're both saying the same thing. So now that'd be it. I mean, you take that information, you can plan your packer tests, your pump tests, screen intervals based on that. That's what you would have traditionally. But as I mentioned, there's one more probe we want to talk about. And let's see if that tells us the same thing or if it tells us anything different. And that's the NMR, nuclear magnetic resonance. Now, before you ask, it's not a nuclear source, so you don't have to worry about losing the radioactive source in the hole. It just measures properties of the nucleus of atoms. So that's what. No, not a neutron. It's not a density source. It's just magnets. And the way it works, I'll go and do it. I can't tell you the exact way because I'm not a quantum physicist, but approximately how it works for human brains to comprehend anyway. All subatomic particles, so that's protons, neutrons, electrons. I won't care about antimatter and all that stuff, just the main ones. They spin. They don't know if they really spin, but they act like they spin. And the charged ones, protons and electrons, if you spin a charge, it's just like putting charge through a coil. It creates a magnetic field, like in a motor. And so if you just spin a charged particle, it does the same thing. So every charged particle, every proton, every electron has a magnetic force. Most of the time, they pair up with other of the same type of particle. So protons in a nucleus, there's always most of the time there's other protons around, and Mother Nature makes them balance it out. So if you have a simple atom, let's look at helium, 2 protons, 2 neutrons, 2 electrons. And the nucleus, you got one that's got a magnetic field that's pointing any given way. The other one's going to pair it with it, and it's going to point the other way. And the same thing will happen with the electrons. So as we all know, helium is not magnetic because these spins are balanced. Hydrogen,
Be able to see that as well?
no, you can't see helium at all, but that's a good thing. Hydrogen has only 1 proton and 1 electron. It's the only atom that only has 1 to choose from. So, it can't balance at all. You might ask, well, can the electron balance out the proton? Well, they couldn't even if they wanted to because their magnetic fields are different strengths. Electrons are actually much stronger, but they don't even get to that option because hydrogen forms bonds. There's never just one hydrogen atom hanging out by itself. And in our field, they bond with oxygen to form water. So those electrons are shared with the oxygens, and they'll balance each other out. So that only leaves 2 particles out of the whole balance. Oxygen's nucleus will be balanced too. So the 2 hydrogens are left imbalanced.
Why is the oxygen considered balanced, whereas the hydrogen isn't? Or is it just that it's,
8 protons, so 4 will be up, 4 will be down.
but then that leaves, okay.
Yeah. So, but yeah, some can have some imbalances, but hydrogen can't have any balance whatsoever. And,
Hydrogen's going to react a lot more strongly than the oxygen.
yeah.
If you're just-
And
the electrons is ballast.
yeah, hydrogen, the nucleus of the hydrogen is the most magnetic of any element. And you might ask, can the hydrogens balance each other out? No, they can't because they're too far apart. Their magnetic fields are actually quite weak, and they can't even tell that the other one's over there. So they're just left unbalanced. So hydrogen is unbalanced and magnetic. In the natural environment, hydrogen is the most magnetic nucleus. There are some other elements that have more magnetic electrons, iron being one of them. A lot of them actually have imbalances in their electrons, but in terms of the nucleus, the hydrogen is the most imbalanced. And I actually have to switch to a different mode to show you a video. So So,
So the way that magnetic resonance works, it's almost like striking a bell.
well, I haven't gotten into that yet. That's what the videos are for.
You're gonna do something to hit it, and then you're listening for the response.
Yeah, you're pretty, you read the book already?
Almost like I'm thinking of it like you do with audio,
Okay.
listening for an echo. Is that what you?
Kinda, I mean, not exactly, but I'll show you the video. So hydrogen magnetic fields, we're just gonna look at some hydrogens in an area that we're measuring with the probe. They're just gonna hang out here. They're gonna have magnetic fields that are gonna be represented by arrows. And they're gonna move all over the place because they're imbalanced, they're just going any which way, and actually those electron fields are just gonna be moving around and just bouncing them about. So they have no control over where they're just getting pushed around by electron magnetic fields.
I would have thought that whatever way they were spinning, if they are spinning, they just continue to spin the same way all the time.
Well, because the electron fields are so much stronger, they would, if they were left on their own, they'd keep spinning, but they're just constantly being nudged.
Oh, just by.
Stray electron, imbalanced electron fields. It's like magnetic noise that's just always making them move around.
Kind of like static on the radio.
Yeah, that, very much. So, but if we put a constant magnetic field, they will respond to that and they'll line up. And so you'll see they'll gradually respond to that and will point the same direction. Once they're all pointing the same direction, just for simplicity, you can just represent them as one arrow because they're all pointing up parallel to that magnetic field. That's the same slide. Okay, so then how do we measure porosity? We take another magnetic field and we go in at 90 degrees and we oscillate it back and forth. Remember, they're all spinning. So if you time the oscillation to the same frequency that it's spinning, it'll react with it and it can actually tip it into the plane of the magnetic field. And this is actually from an electromagnetic wave, which has magnetic fields that are oscillating back and forth. So what it'll do is that spin will start to tip once you find the correct frequency. And if you rotate a magnetic field, just like if you rotate an electrical charge, it'll create a magnetic field. If you rotate magnetic, it'll create an electrical response, and you can measure that over here. And so the amount of electrical response we measure is just a function of how many hydrogens are spinning. And in our environment, hydrogen is pretty much always just bonded to oxygen to form water. So we can measure the volume of hydrogen, which is the volume of water, which we call porosity.
What's the frequency? Are you looking for what the frequency is, or what's the spike on that represent?
That means that that's actually the next slide. Let me show you.
Okay.
So, as he asked, the frequency, what do we know what the frequency is? The frequency of a hydrogen spinning is controlled by the strength of the field. So if you increase the field strength that you just saw there, it speeds up. If you decrease, it slows down. Now, you're asking, how do you find the field strength? How do you find the frequency? Well, we know how strong, just from experiments, we know how strong the frequency of hydrogen in any given magnetic field. And we know how strong our magnet is. And crucially, you know, if you move away from a magnet, the magnetic field decreases. So we know how strong the magnetic field on the probe is going to be here, 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 here. And from those experiments, we know how fast the hydrogen is going to be spinning here, 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 here. And so we can use that oscillating frequency to interact with only one distance of hydrogens.
So as you increase the frequency or increase it, maybe, I don't know, then you're going to get measurements
Further apart, yeah. So we can just use whatever frequency we want, and we can interact with the hydrogens. You could do it in the borehole, but we don't care about the water. You could do it right beside the borehole, but then you're probably going to have, if you got a little bit of a fracture or breakout or something, you're going to be measuring water. You put it so it's far enough out in the formation that you're beyond the borehole, so there's no borehole effect. Like with the resistivity, where you've got the mud that's affecting the nearer electrodes, there's nothing with the magnetic resonance.
So how far out do you usually go?
Depends. There's different probes for different distances. The deepest one, I think it's like 20-inch diameter that we run. I mean, if you want to go to Schlumberger, they probably have a bigger one, but it'll cost you an extra zero on the end. So,
Of course, typically, I mean, whatever your porosity is, say at 1 foot or 2 foot or 5 feet from the hole, if you went 10 feet from it, it's probably roughly the same.
same, yeah. I mean, the drilling effect. I mean, unless your hole is really horrible, it's not going to affect that far out into the formation. You know, from the grinding up the hole or fluids getting in, it's pretty near hole. So this is you can measure beyond the hole. You don't have any hole effects. The last thing, this is where the resonance comes in. We turn off the oscillating field. Since they're rotating in resonance with each other and they have angular momentum, it's just like a top. You spin it, it keeps going. And it's going to keep spinning until something, I mean, a top will eventually die out, but let's say it's a perfect, no gravity, and top will just go forever. But if you perturb it, if you flick it, the top on your table, it's eventually going to start to wobble, and then it's going to tip over. Well, when we turn off that oscillating magnetic field, the electron forces that made it all noise just dancing around in the first place, they're going to mess with it and knock it out of that plane, and it's just going to go back, because we never turned off this magnet. That's a permanent magnet. That's just a hunk of iron.
That one would have, what you were saying before is that one is what's inducing them all to spin the same direction in the first place. So I think
Yeah.
once you turned off the oscillating one,
They're going to go back.
they're going to go back.
Yeah,
Whether
and
there's
if
any noise or not.
well, no, because actually, since their forces are 90 degrees to it, that it doesn't interact with it. If you got a magnetic field pointing this way and one going perfectly, they're not going to affect each other. But as soon as you knock it off, it's going to start to feel it, and you knock it off that perfect plane from all those stray electron forces. And so, and as you saw there, as it comes off of that plane, that response decreases. And what controls how fast that signal decreases? It's how many electrons are around it, and that is a function of pore size. So if you got tight little pores, then you're surrounded by rock with all these stray electron fields. If you got a big pore, you are surrounded by water, and you barely feel the electrons. So that decay will be slower. So this tells us pore size. And these are my backup slides in case my videos didn't work. Let me skip ahead. Okay, so we're almost done. Let's interpret that log again now with the NMR data. So here's the same one. We've got the gamma, we've got the resistivity. They're showing the same things. First, let's look at just the total porosity, the first part of the NMR reading. It's kind of helpful, but overall, the porosity is kind of steady in this hole. Here's this high resistivity zone, low gamma, where we thought we'd have good transmissive rock. Yeah, porosity is a little higher there, but here's a shale, low permeability. It's a little lower. The reason for that is shale can have porosity. It's just that they're so small that they don't transmit water. And so, just by the way, you mentioned neutron log. This is what you get from a neutron log, just a total porosity. It's kind of helpful. There's your highest permeability zone. There's a spike in porosity, but it's not particularly that much higher than anywhere else. Here's that thick zone, as I already explained. A little higher, but not much value there. But now, let's look at the pore size information. So this is the raw data, and I just want to show it to you. What you're looking at is T2, time. T is time. 2 because it's the second half of the measurement. So shorter times are on the left, longer times are on the right. The decay time, if it's longer, it's bigger pores. So what we want to see in groundwater is, well, these colors are the total porosity for that pore size. So you want to see bright colors to the right, because that means you got a lot of porosity and it's in free-flowing pores. That's tricky to look at, and so we make it much easier to look at by binning it up into 3 categories instead of one continuous spectrum. So to the right of this yellow line is free water. It's in a pore that's big enough that water can just flow right through it. To the left of the green line is clay-bound water. So that's in the teeny tiny clay pores being held in place by those electrostatic clay surfaces. No way you're ever getting that out. In the middle is capillary bound. So that's not in clay, but it's in tight little clean pores, but like a siltstone, for example, very fine-grained, tricky to get out. You could get some out if you're going to pump on it hard enough. You can get some out, but don't want to count on that. So when we factor in this information, that total porosity becomes 3 different contributions. The dark blue is the free water. The light blue is the capillary bound. The brown is the clay bound. And let's see how that compares. So clay, brown stuff. Are we seeing that where we get high gamma ray? Yeah, we are. So the gamma is saying you got a lot of clay there. Well, the NMR is saying you got a lot of clay-bound water there. Makes sense. Dark blue, free water. Here's that big, thick transmissive zone. Low clay, high resistivity, clean sand, should have a lot of flow there. And true enough, NMR says you got a lot of free water there. So, great. It's telling me the same information. Why'd I pay for it? Well, I forgot to say one thing. You can calculate the permeability from this. The permeability is just a function of the porosity and the pore size. So basically, this permeability is just going to mirror the free water curve. It's going to account for a little of the capillary water, like on the nearer side, the bigger side, because really this is all a continuous spectrum. We just conveniently put it into 3 categories. But basically, it's going to show what your free water is showing. So that's that thick zone. They're in good agreement there. Yep, it's free-flowing water. How about that clean zone that was the cleanest in the entire hole?
Don't look very good.
Yeah. Well, look at that. Look at that permeability. Almost nothing. Why is that? Well, look at the water. There's a little bit of free water. There's not much clay, so yeah, the gamma wasn't lying. Not much clay. And the resistivity wasn't lying because that responds to clay content, but it's all capillary bound. That is just a really tight sand, siltstone really. So, am I saying don't test it, don't pack her to that zone, just put blank casing over it, forget about it? No, you're probably still going to test it. But if you get a low permeability, you're not at least thinking, well, did I screw up the test? You're saying, okay, well, that makes sense. Now I got 2 pieces of information, NMR and my test that's saying that's not the best zone. So one significant exception with the agreement there. So the takeaways, NMR gives you porosity, gives you pore size, distribution, permeability estimate. It only interacts with, well, I said water there. I should have said formation water. Doesn't interact with the borehole. Oh yeah, water, because it doesn't interact with the minerals. It only acts on the hydrogen in the water. You can run this through PVC. You can't run it through metal. That'll mess with all the electric signals. You can get a permeability before you develop the well. You don't have to develop it to run your packer test. You can just run it in your mudded up hole because it's getting beyond the mud invasion. Fresh or saline, doesn't matter, whereas resistivity doesn't work very well in saline water.
Can you show us that last slide again?
Yep.
So why would we not do this instead of the gamma? It looks like this gives us more and better information.
Yeah, well, you never really want to have 2, or you want to have 2 pieces of information. The truth is, You can do them both on the same run. Might as well. Yeah. But, you haven't done it historically because it is more expensive. It does run slow. And it just hasn't been available for groundwater, it has kind of been available. I think it's just a budgetary thing. It was developed in an oil field where Schlumberger, where you're going to pay them extra $0 or $2. But there's new companies that have waited for patents to expire and stuff and made their own probes. And they made them smaller because the Schlumberger one's about that big. And they want to use this in the mining industry or, test holes for groundwater. And you just can't fit it in there. So it's only been, 10 years maybe that there's been miniature versions that you can run in smaller holes. Yeah, and that's where I plan to leave it off. I got other examples, but I think I'm probably out of time. This is just comparing with a Packer test. Pretty good comparison there. But if anybody's got any questions, we might not have time, but you can always catch me in the breaks if we have time for any breaks. Thanks.
Thank you.
Thanks, McLain.